Chapter 13 itself is an introduction to functions of several variables. What we will do in chapter 13 is actually mimic calculus 1. Calculus 1 is the investigation of a function in one variable. Y depends on x. F of x is equal to something. We find all of the neat properties of derivatives and that type of thing. That's how we began with calculus 1. And then after we investigated the so-called properties of differentiation in calculus 1 on a function of one variable, then we next looked at integration of a function of one variable. So this is the same paradigm that we use. Chapter 13 is the investigation of differentiation of functions of several variables. Chapter 14 would be the investigation of functions of several variables with respect to integration. And so here we talk about all of the properties associated with differentiation for functions of several variables. We take the derivative of a function that depends on more than just x. And in doing that, it is necessary to talk about what we call a partial derivative. I can take a derivative of a function of several variables, but just focus on one of those particular variables, leaving the other variables constant. But we began in this section by giving the definition of a function of two variables. We make this the structure by which we can talk about functions of even more variables, independent variables than just x and y. Typically in nature, this is basically all that we have, but it is possible to have another independent variable acting on z. So the definition here of this function of two variables is basically identical to the definition for the function of one variable, but here, instead of saying y depends on x, z now depends on x and y. So we let some superset D be a set of ordered pair that consists of real numbers. We don't here for this definition talk about the set of complex numbers. We do that in another course, complex analysis. If to each ordered pair x, y, we make an assignment of a unique number. There corresponds to each ordered pair some unique number we call an assignment. Here, this number is called z. Then we say that f is a function of x and y. The so-called domain we have some domain and then the so-called range. Even a better phrase for range nowadays is codomain. So what the function f wants to do is to find ordered pair in the so-called domain and map or assign to some unique number over in the range or the codomain here that we'll call z sub 1. And then it wants to take other ordered pairs as well and continue the assignment. Now we stop there. We don't go any further by talking about the true nature of the function Hopefully that is to be understood from your study of functions of a single variable. That is that if this is to be a true function, I cannot have the second ordered pair here somehow being mapped to another uh, range value. Uh, we would say then it wouldn't be one-to-one. Um, so let me put this in blue. If I had x sub 3 comma y sub 3, it is possible to have this guy mapped to z sub 2. That's fine. That's still a function. But I could not have x sub 3, y sub 3 mapped to a z sub 2 and also a z sub 3 at the same time. I can't split this nature going from the domain to the range. I can't have this guy x sub 3, y sub 3 also mapped to some other range value. It wouldn't be a function because we say here that the z sub 1s, the z sub i's are supposed to be unique, and if that's the case, then it wouldn't be unique. So this is good. I don't know if you recall whether it was high school algebra or even in Math 112, you had to investigate whether or not a domain or a set of points for x and a set of points y, if they constituted a function or not. Let me say this quickly and then we'll move on. For example, if you had y equal to x squared, or you could say f of x is equal to x squared. The question is this a function? It's a function. If, say for example, you take x to equal to 1, we get 1 here. You take x to equal to negative 1, you get 1 there. That's fine. 2 goes to 4. Negative 2 goes to 4. Let's look at that. So here I have 1 goes to 1. Negative 1 goes to 1. That's the same thing there. That's fine. Two goes to 4. Negative 2 goes to 4. That's good. Yes. It wouldn't be one-to-one, but it's a function. One-to-one. That is that for each domain value, it maps to only one range value. That's one-to-one. So x sub 1 goes to y sub 1 only, right? X sub 2 goes to y sub 2 only, right? That's one-to-one. This is not one-to-one, but it's a function, right? You recall that we said that a function has an inverse if it's one-to-one, right? And you would use the so-called horizontal line test to determine whether or not it's one-to-one. But to determine if it's a function, you use the vertical line test. Right? So if that's the case, then what about I think this should do it. X equal to y squared. Sir? The horizontal line test was to determine whether or not the function is one-to-one. That is, if it has an inverse. If it's one-to-one, then it has an inverse, and we can find the inverse of that function. You take a vertical line and you draw a vertical line through the graph. If the vertical line crosses the graph more than once, then we say that that particular relation is not a function itself. Right? So if you take this guy, here it's easier to pick values for y, or you can write this as y equal to plus or minus the square root of x, right? So if you pick, let's say y equal to 1, then y squared is equal to 1. If y is equal to negative 1, then y squared is equal to 1. Right? So here I have 1. This is for my domain. One here is mapped to 1, but then 1 here is mapped to negative 1. This relation is not a function. If you look at this graph, if you take the vertical line test, the vertical line crosses it more than once, so it's not a function. So function is defined as the old definition, a set of order pair where no two order pair have the same domain value. So this is 1 to 1, 1 to negative 1, but they're the same, so you can't have that. Right? If you wrote it like, if you wrote the order pair, this is 1 and 1, and then 1 to negative 1. A function is said to be the set of order pair where no two order pair have the same x value or the same domain value. Right? So all of that is to be understood when we talk about functions. And now that's that's what we know. Well, okay. And so now we talk about functions of several variables. That is to be assumed and understood. So we have that same nature going on. We'll look at in just a minute functions of several variables. We want to examine the so-called domain and range and see how that works out. Okay. Evaluate this function. Let me give you a heads up of what this is. We're trying to get prepared to find the partial derivative. Here's what this guy is saying. This is not a limit, so it's not a derivative yet. If I put a limit sign in front of it and say as delta x goes to 0, then it becomes a limit. Without that, it's just the slope of a secant line. Look at what it's doing. It's investigating the change of x, but it's keeping y fixed. See that? X's are changing. That's that delta x, right? As x changes a little bit with respect to some delta, a very small movement. what happens to the function? Keep y fixed. When you do that, what you actually find is the derivative of f with respect to x only, and we keep y fixed. That's a partial derivative. So this is the setup for it. Now, if you look at that function and take the derivative of this function with respect to x, you would expect to get 6x, treating y as a constant or coefficient. So here, what we do is we find f of x plus delta x comma y minus f of x y all over delta x, yes, is equal to 3, where I have x, I write x plus delta x plus delta x to be squared minus 2y. Now this is now minus f of xy, that's bracket 3x squared minus 2y all over delta x. So we simplify that. This is 3 times x squared plus 2x delta x plus delta x squared minus 2y minus 3xy plus 2y all over delta x. Now the 2y's there cancel out. So we simplify that, the parentheses. So this is 3x squared plus 6x delta x plus 3x plus 3 delta x squared, minus 3x squared all over delta x. Now the 3x squares cancel out. I have left 6x delta x plus 3 delta x squared all over delta x. Factor out delta x from the numerator. This is delta x times 6x plus 3 delta x divided by delta x. Delta x divided by delta x cancels. So I have left 6x plus 3 delta x. Again, we're not finding the limit, we're finding basically the slope of the secant. The limit would be if you send delta x to 0, you end up with just 6x. Right? So this is the answer just for this problem, but notice here that that this term here goes to 6x as delta x goes to 0. And later on, we ask for the partial derivative, then that's what we'll be looking for then. But for now, this is all we want. That's the slope of the secant. This is what we just found. Okay. Put the limit in front of that, and then you get the slope of the tangent. What do we mean by the secant? The secant is simply a line that crosses a curve at 2 points. Pardon me? If I take the limit of this ratio, take the limit of that, then I get the slope of the secant. That's not what that is. Thought it was a y square there, it's not. just come down here and just show on the side, if you will. We call this a secant line. Just any line that crosses a curve at 2 points. If I investigate at this point some line that touches only at 1 point, then we call that a tangent. Hence is where you get the derivative from, right? Okay, let me move on. Only have 15 minutes. Let's look at domain and range. Find the domain and range of this particular function. Here, the domain would be all x and y values that define this function or that gives z a value. Well, you notice that if it's a fraction, then what needs to be investigated is what's happening in your denominator, right? You don't want your denominator to equal to 0. So here, your domain, anybody have an idea? That's right. So here, our domain is said to be the set of all xy ordered pair such that, this line means such that x cannot equal to 0, comma, or y cannot equal to 0. What about the range? That would be the set of all z values, right? Is there any restriction on z? In terms of restrictions, you argue on the number line, can z be negative? Can z equal 0? Can z be positive? Right? If you can answer all three yes, then z is all real numbers. Right? So set of all values for z, you can write it from negative infinity less than or equal to z less than or equal to positive infinity, or you could say z is any real number. What's the domain and what's the range for this one? So no negative values for y, is that right? Okay, I mean that's good, that's good. Or you could say that y has to be what? Greater than or equal to 0, right? Yes, sir. That'll be the only restriction, right? And then what about the range? What would the range values be? All real numbers. You get a restriction on y, but x can be any number. So x could be negative times a positive number. You still get negative numbers, right? So you get negative, positive, and then also x or y could equal to 0. So for the range, it could be negative, positive, or 0. Very good. So this is the domain. Where did the range go? For all z, Z can be any real number. Find the domain and range for this function. The domain would be what's in that radical would have to be positive. So you know that 4 minus x squared minus y squared has to be greater than or equal to 0. I'm going to add x squared plus y squared on both sides. So that is x squared plus y squared is less than or equal to 4. That becomes my domain. So the set of ordered pair such that x squared plus y squared less than or equal to 4. What about the range values? The result of that square root is what? The image of the square root values are what? Positive, right? Right. So, I mean, one way you could think about it, if let's say that here z is equal to f of xy, if you want to investigate it. So this becomes z squared is equal to 4 minus x squared minus y squared. This implies that x squared plus y squared plus z squared is equal to 4. Now what is this guy right here? It's a sphere, right? It's a sphere, yeah, a circle in the 2 space, and a sphere, a basketball in the 3 space. It's a basketball, but remember this z is supposed to be representing f, right? Z is equal to f of xy. So it's a basketball, but it's not the whole basketball. It's the top half of the sphere. What's that top value up here? What's that number? What is that number? What's the radius for the sphere? So z goes from what value to what value? 0 to 2. That's the range. It's kind of better, I think, when you can see the graph of it and see what's happening. Find the domain and range of the function. I want to say we introduced the inverse trigonometric functions on page 373 in your textbook. Recall that if y is equal to cosine x, then x is equal to cosine inverse of y. If you have y equal to cosine x, then we want to determine the domain for x, thus giving us the range for y. Well, the way we answer that is that you know that here cosine hovers between -1 and 1, right? So -1 and 1 becomes what? Your range or domain? Becomes the y values. That becomes the range, right? So let's look at that. So here I have the domain, here I have the range, and what we're investigating is this y equal to cosine x. So we know that the range goes from -1 for y to 1. Right? Well, that gives us x values go from x to pi. Now, if that's the case, then notice here that this becomes z. So z then acts like y down here for y equal to cosine x. And this x acts like x plus y. Right? But you want to flip it because we're now dealing with this guy here, right? So you think about this as if and only if cosine z is equal to x plus y. So now with that in mind, x plus y is between what and what, and then z is between what and what. Yes, sir. And then the z is between, all right. So this x plus, I'm looking at this x plus y over here, thinking about cosine. So this x, cosine x equal to y, right? Whatever's in this position here, cosine of something, that guy goes here, right? This is cosine of z. So z is between 0 and pi. And x plus y is in between -1 and 1. This becomes our domain for the function at hand, and this becomes the range for the function at hand. I just match them up, that's all. Right? All right. What about this guy? Well, it's good to know and recall the definition for the natural log. Definition for y equal to the natural log of x. We say that this is if and only if e to the y is equal to x. Now, when I investigate just this function y equal to the natural log of x, to determine the domain, that is the x values, and then the range, the so-called y values. Notice here that the y values up here, e to the y, these y values can be anything, right? These y values there can be any real number. There's no restriction on y. So here, not 0, but negative infinity is less than or equal to y less than or equal to infinity. Now x, that's where I have the problem on x. X cannot be certain numbers. Do you know what they are? Well, I'm not thinking about this guy for right now. I'm looking at just the definition. So from the definition, I can build the range and domain. But here, this x here, very good, very good. So here, this domain for x, because if I take e is fixed, a fixed number, and then raised to the y, then the result of that is always positive, right? As a matter of fact, it can't even equal 0. It could be very close to 0, but it cannot equal to 0. So here, for my domain for this x, these guys would be x is greater than 0. So if that be the case, then that also means for this function at hand, my domain, these guys right here, 5 minus x minus y, would represent this x here. So this term here has to be greater than 0. So for our domain, we have 5 minus x minus y is greater than 0. Sorry, greater than 0. Well, that is x plus y is less than 5. So the set of ordered pair x, y such that x plus y is less than 5. And then for the range, just like the range over here could be all real numbers, the range here for f is all real numbers. Okay, yes, sir. If you wrote it as what? Yeah, that's fine too, but if you wrote it as 5 minus x minus y is greater than 0, I mean, that's fine. Yeah, but you want to show me that, you understand what's going on. So, yeah. Yes, sir. All right, good. Well, I'm going to stop here. It's 9 o'clock, and I'll finish this on tomorrow.